Hello, welcome to the second week of recitation for EE2423 Network Theory. On this occasion, I will be solving three problems on basic circuit, and let's get started. So the first problem is given as follows. So you have a very simple circuit. We have a independent voltage source, VG, and it is connected to a single resistor. Let's just call it with R, and that's it. Very simple, right? And define the current flowing through the circuit as IG. So we have some set of questions, and the first one is VG is given as 1 kilovolt, IG is given as 5 milliamps, and the question is what is R and what is the consumed power by the resistor. So PR, power at resistor. The second set is IG is given, so 75 milliamp, and this time the voltage source power is known, so the power produced by the voltage source is given as 3 watt. Okay, and the question is what is VG, what is R, and the power consumed by the resistor, which is PR. Okay, the last set of questions, R is known, given as 300 ohms, and the power consumed by the resistor is given as 480 milliwatts. Question is what is IG and what is VG. Okay, so let's solve the first one. So the basic formula that we will be using is the Ohm's law. So Ohm's law, so V equals I times R. So V is the voltage, I is the current, R is the resistance, and basically this is the equation that we need to solve this problem. Okay, so we'll put that in box. Okay, for the first one, A, what is R? So R, from Ohm's law, we know that R is V over I, right? So this time V is the VG, of course, I is IG. So 1000 volt, which is 1K, and 5 milliamps, so 5 times 10 to the power of minus 3. Okay, so we have 200,000 ohms or 200k ohms. How about the power consumed? So PR is, so the power, okay, the equation for power is, so power P is equal to VI, so voltage times the current. Okay, so V here should be VR, right? The voltage at the resistor, and I, the current at the resistor. But we know that current flowing through the resistor is the same as IG, so just IG. But VR, so what is VR? VR, using the Ohm's law, you know that VR is IG times R, right? So IG times R times IG, we have IG squared times R, right? So IG, which is 5 times milli, is 10 to the power minus 3 squared times r. So r is 200k 10 to the power 3. So we get which is 5 watts. Okay, so another way you can compute PR is just Vg times Ig. Okay, because the voltage on the resistor is the same as the voltage coming from the voltage source, so you just compute Vg times Ig. So 1000 volt times Ig is 5, so it gives you the same 5 watts. Okay, the next set B, what is Vg? Okay, Vg is, so we will be using the equation for power. So Vg is P over I, but since the power from the voltage source is a delivering power, so the signs will be negative. Okay, so that's the convention. If any unit is giving power, then the power sign is negative. If anything is consuming power, then the sign of power is positive. Okay, so that's the convention here. So following that convention, then I should put negative sign there. Okay, Vs over Ig, so minus 3. This is 3 over Ig is 75 milliamps, so you'll get 40 volts. How about R? For R, we'll be using the Ohm's law. So R is Vg over Ig, which is 40 over 75 milliamps. It is equal to 533.33 ohms. And what is the consumed power by the resistor? So the consumed power PR is, so assuming that the system is ideal, meaning that there is no losses whatsoever. So in most of our analysis, we are dealing with ideal circuit. Okay, so there's no losses on the system, so we're assuming that all components are working at 100% efficiency. There's no power losses. Okay, in that scenario, or with that assumption, then the consumed power PR is equal to minus of the given power, so minus PS, so minus 3, which is 3 watts. All right, C, the question is what is Ig? Okay, so we know from this equation here, so PR is Ig squared R, right? So that means Ig is square root of PR over R, which is square root of PR for 80 milli. R is 300, so that equals to 40 milliamps. The second question is Ig, so it's Vg. So Vg, we can use Ohm's law directly. I times R, so Ig times R. Since Ig is 40 milli, so 40 times 10 to the power of minus 3, and R is 300. So that gives 12 volt. Okay. Alright, so we have finished the first problem. It's very simple. We just need to use the Ohm's law and the power equation, then everything is solved. Second problem, a little bit complicated, and it's given as follow. So we have a circuit again with independent voltage source. This time is given as 200 volt. We have a resistor. This is a mysterious resistor, which is we do not know the resistance, but we have two other resistors. This one is 24 ohm, the other one is 8 ohm, and our job is to find what is R here, what is the value of this mysterious resistor. But you cannot be solving this problem this way because we need something. There's something that is missing here. So it is specified that the voltage on this particular resistor is 120 volt. Okay. So let's call this one is R1, call this R2, and to solve this, to find R, then not only we need to use Ohm's law, but we also need to use Kirchhoff's law. So either Kirchhoff's current law or voltage law, so KVL or KCL. We will be using both of them actually, Kirchhoff current law and Kirchhoff voltage law. So for this type of problem, I prefer to use KVL first, so the Kirchhoff voltage law. So let's draw a loop here and another loop there, and let us define the current flowing on this loop is, so let's call this is L1, which is loop 1, L2 loop 2. So the current flowing inside the first loop is I1, right? And the current flowing on the second loop is I2. So okay, that's what we have right now. We know that VR1, so voltage at R1 is 120 volt. Okay, so let's write the equations for both loops. At L1, what we have? We have minus 200 volt, right? So the loop is in the clockwise direction, so we have minus 200 volt first, and then we have plus I1 R. So I1 we do not know, R we do not know, plus the voltage. Okay, we have the voltage there, right? 120 volt must be equal to 0. So that's the Kirchhoff voltage law. The sum of voltage around a closed loop circuit must be 0. So the sum of voltage around any closed path or closed loop is 0. Second loop, we have minus 120, right? Plus I2, second current, times the resistance there, 8, equals 0. Okay, so we can compute I2 directly from here, right? So I2 is 120 over 8, right? It is 15 amps. Okay, we need another equation to solve it, and this equation comes from this R1 resistor. So what do we know about that? So we know that from the Ohm's law, from R1 resistor, we know that the voltage, which is 120, equals to the current at R1, so IR1 times the resistance, right? 24. But what is IR1? But IR1 is by this loop. So the way we define the direction of the loop, which is clockwise for both loops, you know that IR1 is nothing but I1 minus I2, right? Which is 24. Okay, so I1 minus I2 is 120 over 24, right? Which is 5 M. Since we know I2, then we can compute I1, right? So I1 is 5 plus I2, 5 plus 15, which is 20 amps. So we know I1, right? Okay, so we can use the first equation there. From the first loop, we have I1R equals, bring the voltages here to the other side, we have 200 minus 120, which is 80. So R is 80 over I1, 80 over 20, which is 4 amps. Sorry, A is resistor, so it's not ampere, it's ohm. Alright. Okay, so the resistor there is 4 ohm. Alright. Problem number 3. It is more complicated than the last one. Okay, so I have this 5-volt independent voltage, resistor 54 kilo ohm, another source 1 volt, we have resistor 6k. Alright, interestingly, we have dependent source, dependent current source, that direction, and so the voltage across this dependent source defined as V, which is we do not know, and the amount of current generated by this dependent source is 30 I1, whereas I1 is defined as the current flowing through the 54 kilo ohm resistor. So we have that I1 on that direction, particular that direction. Okay, and we have another resistor 1.8k, another independent source plus minus 8 volt, and that's it. Okay, well, so what are the questions? First one, find I1. Okay, question B, find V, so the voltage at the dependent current source. C, what is the total power generated. D, total power absorbed or consumed. Okay, for CD, you should know which kind or which type of units that are generating power, right? So we have sources. So sources like the voltage source and the current source, they generate power, obviously, and the resistors, they consume power. right? So when you are computing the total generated power, then you need to compute the power generated by each of these dependent and independent sources, and for the consumed power you need to compute the power on every single resistor. Okay, so let's solve for I1 first. So for A, to solve it, let's use the KVL. Again, we draw two loops. Since we have already defined the current flowing at this particular loop as I1, so we know that the current flowing from this loop is I1. Okay, so we have I1 there. This one doesn't have any definition yet, so let's assign I2. But what is I2 there? We know that I2 is the current flowing here on clockwise, right? Clockwise direction, which is I2. But we know that the current uh, given by this dependent source is 30I on the opposite direction. So fact. So what do we know? Let's say, or let's just facts, things that we know, which is, so I2 is equal to minus 30I. Okay, from the first loop, so say L1, L2, L1. At L1 we have what? We have minus 5, right? Plus 54k, so 54,000 I1 minus 1, right? 1/4 plus 6k. The current, what's the current there? The current there is I1 minus I2, but I2 is minus 30 I1, so you can substitute I2 with minus 30 I1, right? Equals 0. So we can simplify this. We have minus 5 minus 1 minus 6, right? And then plus 54,000 I1 plus, this is minus minus, we have plus there, so 31 I1, so 6,000 times 31 I1 equals 0. We can simplify further the equation, so you get the expression for I1 is 6 over 240,000, which is 25 microamps. So I1 is 25 microamps. The answer for A. How about B? We need to analyze the second loop to find the answers for B. Okay, so what's the voltage there? So we have, starting from here, we have V, right? So because we already defined the voltage on this source as V, so V plus 1.8k, so 1800 times I2. So what is I2? I2 is minus 30, so it's just right, minus 30 I1. Okay, and then we have that source, voltage source, plus 8 plus 6k, so we have 6,000. The same equation here, I1 minus 30, let's just write plus 30 I1, 0. Okay, so you can simplify to V minus 54,000 I1 plus 8 plus, you can multiply this, right? 6000 times 31, the same thing here, so it's actually 186,000. I1 equals 0, you know I1, right? So phi is again 24 240,000. I1 is times 25 micro is 10 to the power of minus 6, and then oh, I apologize, I just made a mistake here. So we have that plus sign here, right? Because the current is flowing to that direction, so we have plus minus there, plus minus. But for the second loop, it has minus first, so this will be minus. Should be minus, right? So you have minus. Minus minus, you have plus actually, but this one is minus, so you have minus 2 volt. Okay, C, so we need to compute the generated power for its individual sources. Let's start with the 5 volt source. So 5 volt, remember that for generated power the sign is negative, similar to this one. So P is Vi, so minus Vi. V is 5 volt, and the current is flowing through here is I1, so 25 microamps. 10 to the power minus 6 is minus 125 microwatts. Second source is the 1 volt voltage source, same, minus 125 microamps, same, minus 25 microwatts. For the 8 volt, you have minus 8, but the current is 30, right? 30 times 25 micro, which is minus actually 6000 microwatts. And the dependent current source, the voltage is 2 minus 2, the current is 30 times 25 micro, which is minus 1500 microwatts. And why is the total generated power? You sum everything here, I get 6150 microwatts. So all of these sources combined, they generate around 6150 microwatts, which is around 6.15 milliwatts. How about the consumed power? Okay, we have the 54k resistor, so we'll be using this equation here. So the consumed power for resistor is I square times R, so I at the 54 is I1, so 25 micro, so I squared, right, times 54k, which is 33.75 microwatts. The next resistor, the 6k, you have this one here, 31 times 25 micro square times 6, okay, is 3603.75 microwatts, and the last resistor is 1.8. Same thing, so you have 30, right? 30, because it's I2 here. I2 is 30 I1. 30 I1 is 30 times 25 micro squared times 1.8 is 1012.5 microwatt, and then if you sum all of them, you have 6150 microwatts. So that tells you that the generated power is the same as the consumed power. So in ideal circuit, the total generated power should be equal to the consumed power. Okay, so that tells you that your solution is correct. Okay, so I think that's the end of this recitation class. If you have any question, please come to my office hour on every Tuesday at noon, or just send me any email. All right, see you next time. Thank you.